So now as we get into our second section of Module 11, our Module 11-2 here, this is going to be a review of our Chapter 6 content, looking at the introduction to convection. So within this review, we're going to take a look at the topics of mass transfer, boundary layers, and dimensionless parameters. Now within this, we're going to go through the theories that we covered before and review those, review some of our governing equations, talk about some of the practical applications, and then we're also going to go through some new problems for my hand solution as well. So relating this to our textbook, again, this is going to be a review of our Chapter 6 material. This is going to be our Introduction to Convection, looking at mass transfer. So this is Chapter 6 and our Appendix E that we're going to be reviewing, Sections 6.1 through 6.8, and our Appendix E4. Now, if we're going to introduce this concept of a boundary layer, what we want to do is we want to consider the flow over a plate. And we can see that in this diagram here. We have a flat plate right here with flow over it. Now, when the fluid particles make contact with this surface, the velocity is then going to be reduced significantly relative to the fluid velocity upstream of the plate. So now I want to take a look at our velocity boundary layer. Now with this here, the boundary layer velocity profile is going to refer to the manner in which our U term right here varies with our Y. So you can see our Y coming up off our flat plate right there through our boundary layer. Now with this, the fluid flow is going to be characterized by two distinct regions. The first one being our boundary layer, or a thin fluid layer, in which our velocity gradients and shear stresses are large. And then also we're going to consider a region outside of the boundary layer. And in this here is where our velocity gradients and our shear stress are going to be negligible. So now as we get a further distance away from our leading edge, we're going to see that the effects of the viscosity penetrate farther into the free stream and the boundary layer grows. So what we can say is that our delta right here is going to increase with x, and we can see this in the shape of that velocity profile right there. And this is our term, delta with respect to x. So to summarize our velocity boundary layer, this is a consequence of the viscous effects associated with the relative motion between a fluid and its surface. So that's what we have over here in our diagram. We see our surface and we have a fluid above it. So a region of the flow is going to be characterized by shear stresses and velocity gradients. And we'll get into some governing equations for our shear stresses associated with this. Now, as we mentioned, this is going to be a region between the surface and the free stream. So we have our surface right here, and now we can see right here, we have this free stream right there, whose thickness, there's our thickness right here, our delta, and again, this is going to increase with the direction of flow. So we can see the direction of our flow right here is going in our positive x direction. So we can see that from the arrows denoted there, so that's the direction of our flow. We can see our delta is increasing in the direction of our flow right there. So with this increasing distance, farther from this leading edge out right here, so there's our leading edge right there, the effects of our viscosity penetrate farther into that free stream, and the boundary layer again is going to grow. So again, our delta is going to increase with our x. Now our velocity boundary layer is going to be manifested by a surface shear stress, or tau sub s. Now this is also going to provide a drag force, or F sub d. So this surface shear stress, or tau sub s, is given by equation 6.2 in our textbook. So we have this relationship here, and we can see our F sub d is right here. So for our surface shear stress, if we're assuming a Newtonian fluid, the surface shear stress may be evaluated from the knowledge of the velocity gradient of the surface. And that's what this equation right here, 6.2, is, where this mu right here is a fluid property known as our dynamic viscosity. Now in the velocity boundary layer, the velocity gradient at the surface depends upon that distance x from the leading edge of the plate. Therefore, our surface shear stress and our friction coefficient will also depend on this value for x. So now that we've discussed the velocity boundary layer, let's take a look at our thermal boundary layer next. So this thermal boundary layer is going to be a consequence of the heat transfer between the surface and the fluid right there. So again, there's our surface and our fluid, and now it's a consequence of the heat transfer between those two. So this is going to be a region of flow that's going to be characterized by temperature gradients and heat fluxes. Now, this is also a region between the surface and the free stream. So there's our free stream right up there again. There's our surface right there, whose thickness, our delta sub t now, because t sub t right here is for thermal. This is our thermal boundary layer right there. This is going to still increase with our flow direction. So again, our flow is moving in our positive x direction. So we can see our delta sub t here being dependent upon x and increasing by this shape right here from our leading edge. So now the question is, why does delta T increase in our flow direction right here? Well, what we can think about here is with our increasing distance from that leading edge, the effects of our heat transfer are going to penetrate further into that free stream, and the boundary layer effects are going to grow. So our thermal boundary layer is going to grow as we go further along in our x direction. So our thermal boundary layer is going to be manifested by a surface heat flux. So this is right here, equation 6.3 right here. There's our surface heat flux right there. Our Q double prime sub S, where S, our S indicates our surface right there. And also a convection heat transfer coefficient, H right here, where H is given to us in our equation 6.5 in our textbook by this relationship that we see here. So now let's ask yourself this question here. If our surface temperature and our surrounding temperature, Ts minus T infinity, are constant, so if this Ts minus T infinity is constant, then how does our Q sub S here double prime, or our surface heat flux, and our H value, our convection heat transfer coefficient, vary in the flow direction if this temperature difference right here is constant? Well, the way we can think about this is, since that temperature difference right here is constant, that means it's going to be independent of our direction x. So while our delta T increases with increasing x, our temperature gradients at the boundary layer must decrease with an increasing x. So therefore, accordingly, the magnitude is going to decrease with an increasing x, and therefore it'll show us that our Q sub S double prime, or our surface heat flux right here from equation 6.3, and our H values are going to decrease with our increasing x as well. So as we continue our review of Chapter 6, let's take a look again at the difference between our local and average heat transfer coefficients. So if we're dealing with the local heat flux coefficients, we have our governing equation given to us on page 380 by equation 6.4, where we can see that our surface heat flux, our Qs double prime, is equal to our H times our Ts minus T infinity, where Ts is our surface temperature and T infinity is our surroundings temperature. So now let's take a look at average heat flux and coefficient rather than our local for a uniform surface temperature. So this is going to relate to equations 611 through 613 on page 382 and 383 of our textbook. So let's take a look at our first equation here for our heat transfer rate. Q is equal to our H bar times our A sub S times our temperature difference of T sub S minus T sub infinity right here. We see T sub S is our surface temperature. There's our A sub S right on that surface as well. And there's our surrounding temperature, T sub infinity. And again, this relates back to our equation 6.12 on page 383 of our textbook. Now that's just this one point right here. What if we want to do this for our total heat rate? So our total heat rate Q can be obtained by integrating the local flux right here all over the entire surface. So if we integrate our local heat flux right here, we can do this with our relationship shown in equation 6.11 on page 382 of our textbook. So we have our relationship here that our total heat transfer rate here, Q, is equal to the integral over A sub S times our heat flux right here from this equation up above there times dAs, which is then equal to, pull out our constant right here, this is our temperature difference right here from this relationship up top there once we plug in, Ts minus T infinity, so our surface temperature minus our surrounding temperature times the integral over As of our H, there's our H again from that top equation up there for local, times dAs. So again, this relates back to our equation 6.11 on page 382 of our textbook to get that total heat transfer rate Q. So this brings us down now to our equation 6.13. What we can see here is that the average and local convection coefficients are related by this expression. So we can see our H bar right here for our average local convection coefficient is equal to our 1 over As times the integral of As times H dAs. So that's how we relate our average H value with our H value right there. And you can see this is that average H that we're plugging into this equation 6.12. Now, in particular, for a flat plate and parallel flow, like we see in our example over here, we can see that our H bar right there, or our average local convection coefficient, is equal to 1 over L. In this case here, we can see L is that length right there, times the integral from 0 to L of H dx as we're going in our x direction right there. And this relates now to equation 6.14 on page 383 of our textbook. And this is for our average and local convection coefficients right there. So you can see that average and our local right there, H bar and our H. So taking a look at table A8 in our textbook, I want to go over some of the definitions. So we have our terms on the left, related variable, and the units. So I know I talked a lot about when we set our setup page for these problems. These are three of the things that we actually want to look at when we're creating that setup page. So we want the variable name, we want the thing that's not included here, the actual numerical value that we're plugging into the problem. We're going to want the units we're using, and we're going to want how it relates back to our problem right there. So here's our variable name. It would have some numerical value assigned to it using these units, and this is how it would relate. What it physically means is relating it back to our problem statement and the problem in general. So if we're looking at this table here, we have our species molar flux. The variable is our n double prime a comma s. Units are kilomoles per second times meters squared. Similarly, we can go down through for our species molar rate, our species mass flux, our species mass rate, our species molar concentration, species mass concentration density, our species molecular weight, convection mass transfer coefficient, and our binary diffusion coefficient. Now looking at all these, quite a lot of terms here, and some of them are very similar. So something like this we really want to pay attention to, especially when we're talking about our units and our variable names. If something's listed out in our problem statement as the species mass concentration density, we don't accidentally want to plug in for our CA when really we want our density function right here, our variable rho sub A right there with different units, because now we're in kilograms per meter squared rather than kilomoles per meters cubed. Meters cubed. So this is something that's very, very important to pay attention to. So having a table like this that we can reference back to double check, make sure we got the term correct, make sure we have the correct variable, make sure we have the correct units before we plug blindly in to our governing equations is very, very important. And I know within this course there's a lot of different terms, a lot of different variables. It's easy to get them mixed up. There's nothing wrong with going back to a table, to your reference page, to your symbols list at the beginning of the book, and double checking all of this. So now let's take a look at our species vapor concentration or density. So at our vapor liquid or vapor solid interface, this vapor concentration density corresponds to saturated conditions at this interface temperature, our T sub S. So we have a couple of governing equations. If we take a look here, we go back to our chart, the table on the slide before this, we can see our species molar concentration, our C sub A right there is equal to, now this is at saturated right there, at this temperature interface, this interface temperature right here, our T sub S. Now if we're dealing with density here, we now have our variable again, going back to that table right there, our rho sub AS right here is equal to our saturated density right there at that interface temperature T sub S, which you can plug in for now. We can see here we have our species molar weight that we can plug in times that same saturated species molar concentration at that T sub S right there, or our interface temperature. So now if we were to assume a perfect gas behavior, then the concentration density may be estimated from the knowledge of the saturation pressure, if we have the following relationship that we see here. So this will be our governing equation if this is going to be estimated from the knowledge of the saturation pressure for assuming a perfect gas behavior. Now this concentration may also be directly determined from our saturation table. So another way that we can do this, another way to solve these types of problems, is we can go to our saturation tables. For example, we can look in the back of our textbook and go to our table A6 for saturated water. And we can come up with this following relationship here. Again, if we're looking for the species molar concentration density right here, we have the following relationship here that we can plug into. We take a look now at our free stream conditions. The free stream concentration density may be also determined from the knowledge of our vapor pressure. So again, looking back at our variables here, this is our P sub A comma infinity right here for our vapor pressure. And we can do this assuming, again, still this perfect gas behavior. If we do that based upon that vapor pressure, which we can see right here in the numerator right there, we have this following relationship in order to solve for this free stream concentration right there. Now, if we're taking a look at water vapor in the air, then the free stream concentration density may be determined from the knowledge of our relative humidity right here. So we have our T sub infinity right there. So this is our relative humidity, and this is equal to, now we can see that above there, there's our vapor pressure again, all over our pressure here, saturated at that temperature infinity, which is approximately equal to the following relationship here that we can plug in for. We can see our density right there and our saturated density at that temperature there. And we can also see our concentration over here as well. So this is the case that we can utilize this relationship here if we're looking at a water vapor in air and we're trying to find our free stream concentration. And this is going to be based off of the knowledge of our relative humidity. Now, if we have dry air, one thing that we know here, if we have dry air, this is going to be equal to 0, so we can plug back in up here, and this all equals to 0 in that above relationship. So now let's take a look at our species boundary layer equation and similarity. So we can see here in this diagram we have the development of velocity, thermal, and concentration boundary layers for an arbitrary surface. Now the thing to think about with this is that the boundary layer thicknesses are typically very small relative to the size of the object in which they form, and the x direction velocity, temperature, and concentration must change from their surface to their free stream values over these very small distances. Therefore, the gradients normal to the object's surface are much larger than those acting along the surface. As a result, we can then neglect the terms that represent the x direction diffusion, moment, thermal energy, and chemical species relative to the y direction counterparts. So now if we take a look at our equation 6.25 in our textbook, we can see we have a relationship here for the species boundary layer approximation. So this is given by this relationship shown here. The textbook does a good job of going through the derivation of this as well, so I'd suggest referencing back to this equation 6.25 for review in your textbook. Now the species equation for non-reacting boundary layer is given by our equation 6.30. So what is the significance of these terms within this equation here? Well, the left-hand side of this equation accounts for the net transport of the species A due to a bulk fluid motion or advection, while the right-hand side over here is going to represent the net inflow due to our y direction diffusion. Now let's take a look at our topic of dimensionless groups. So this brings up the point that there's a lot of these tables, charts that we can reference back to in our textbook as we're doing this review of our chapter 6, that we can utilize these for a lot of problems that we're working on and reference back and know where to get this information. So within this table here, table 6.2, this specifies some of the selected dimensionless groups of heat and mass transfer. So within this here, we can see, well, if we're dealing with our Biot number, this has its definition. So we have our relationship here, H times L over our Ks, and our interpretation. So this is great for us. We're not quite sure. It says use your Biot number. Well, what does that really mean? What do I plug in to solve for Biot number? So I can quickly reference back to this table 6.2 and say, well, this is the ratio of the internal thermal resistance of a solid to the boundary layer thermal resistance. So now I understand what it physically is. I have a definition. Well, I have my L and my H given the problem statement. I can look up my Ks from somewhere. So therefore, I can get a value for my Biot number. Now, a thing to mention here, these are dimensionless. So if they're dimensionless and we have the definition to plug into, do out your unit analysis. Unit analysis is going to be very helpful in this situation. You can double check and make sure it truly does cancel out completely and become a dimensionless group here. So we can do this for our Biot number. We have this for our mass transfer Biot number, which is our ratio of the internal species transfer resistance to the boundary layer species transfer resistance. And we have our definition here as well that we can plug in for. We have our bond number, our B sub O right there, which is the ratio of the gravitational and surface tension forces. We have our governing definition right here. We also have our coefficient of friction, or C sub F right here, which is the dimensionless surface shear stress. So right here, we now have our definition for this here, our tau sub S over rho V squared over 2. We have our Eckert number, and this is the kinetic energy of the flow relative to the boundary layer enthalpy difference. We have our definition for this as well that we can plug into. So within these definitions, if we're looking at these, we might know, okay, I know my surface temperature, I know my surrounding temperature. What is my V? Do I have a value for this? Is there some way I can solve this? Is there a chart I can look this up? Was it given in the problem statement? That's why this is great. Also, when we have our setup page, we can reference back to that and see everything that they've given us and everything they've asked us to solve for. And maybe there's another equation that we need to solve for a variable to plug into one of these in order to get our Eckert number or Fourier number, whatever it may be. So then we also do have our Fourier number. We have our alpha T over L squared. This is the ratio of the heat conduction rate to the rate of thermal energy storage in a solid. This is dimensionless time is another way we've seen this before in the past. Then we have our mass transfer Fourier number here. Note the indice down here, M now, compared to our normal Fourier number. This is the ratio of the species diffusion rate to the rate of species storage. And this is dimensionless time as well. And we have last our friction factor here that we're looking at within this. We have our delta P over our LD, or our rho U sub M squared over 2. This is our dimensionless pressure drop for internal flow. So now let's apply the review of some of this governing equations in theory to an example problem. So we'll take a look at our example problem 6.39, and I'll go through this entire example problem with you and show my hand solution. I'd suggest take out a piece of paper and a pencil, have your book open or the PDF of your textbook open and go through and solve this with me. Pause the video as I'm going through my solution. And this is going to be great practice for your exam. And it's going to help you understand where the equations came from, where the theory came from, everything there that I'm doing through the problem. It'll help you reference back and knowing where you can mark your book as you get ready for this exam number 2.
Now let's take a look at problem 6.39. In this problem here, we have forced air at a known temperature of T infinity equals 25 degrees and a known velocity of V is equal to 10 meters per second. This is used to cool electronic elements on a circuit board. One element is a chip. This chip has dimensions of 4 millimeters by 4 millimeters and is located 120 millimeters from the leading edge of the board. Now, experiments have revealed that flow over the board is disturbed by the elements and that convection heat transfer is correlated by an expression of the form shown here. So we have this expression here where we have nu sub x is equal to 0.04 Reynolds number sub x to the 0.85 times our PR number to the 1/3. So this is our expression here. Now we take a look down below at our actual element in our circuit board here. What we can see is we have, okay, there's a length here, 120 millimeters. We have the length of the chip of little l is equal to 4 millimeters. We have the chipboard, the chips. We have over here our velocity and ambient temperature, and we have a direction coming off this edge here of x. So x over to 120 is that 120 from the leading edge, where this is our leading edge, where x is equal to 0. Now we look down below, find that they're asking us to estimate the surface temperature of the chip if it is dissipating 30 milliwatts. Now we've had a chance to read through the problem statement. What we want to do next is look through, identify all the variables within that problem statement, what their values are, and the assigned units. So that's what we do here. We simplify down our schematic, draw this out in a little bit more simplified form where we have, okay, here's our leading edge, this is going the x direction, here's our length L, the location of the chip, this is the size of the chip, given as lowercase l there, here's our board, and here is our surrounding temperature, T sub infinity, and velocity there. So we have this clearly in front of us, not too different than what we saw in the problem statement there, but then I also zoom in a little bit on one chip on the board down here. Now we know they give us a T infinity is equal to 25 degrees Celsius. Our velocity is equal to 10 meters per second. Our lowercase l is equal to 4 millimeters. I decided to convert right away up here to meters, so 0.004 meters. We have our capital L, the distance from the leading edge, of 120 millimeters, or 0.12 meters. We have our nu sub x, given to us in this equation in the problem statement, 0.04 re sub x to the 0.85 times our PR to the 1/3. And we also now have our E sub g dot given to us as 30 milliwatts. So what are they asking us to solve for? They want us to find the surface temperature of the chip. Our T sub s value is what we're looking for. So for this, we need to make a couple different assumptions before we start the solution to this problem. Now, the first assumption that we're going to make here is that we have steady state conditions. We're also going to assume power dissipation within chip is lost by convection across the upper surface only. We're going to assume that the chip surface is isothermal. We're going to assume that the average heat transfer coefficient for the chip surface is equivalent to the local value at x is equal to L, and we're going to neglect radiation. So now we have a nice condensed page here where we have all of our known variables, what the values are, the units that we're going to use, a simplified diagram, what we're searching for, and all the assumptions we're making. So now that we've had a chance to read through the problem statement and write down everything that's given to us, what they're asking us to solve for, and the assumptions we're going to make for the solution to the problem, the next step is to actually begin with the solution and come up with a method. So for our particular problem, the first thing that we need to do is to get the properties of air. So we're going to use the average temperature of air in the boundary layer. And we're going to get this information for the properties from table A4. But in order to do that, the first thing we need to do is assume a temperature for T sub s. Now, this is exactly what we're solving for in the problem as well, so we're going to need to use the assumption in order to compare. So to solve by hand, we're going to need to compare our final answer with the assumed temperature that we're assuming here for T sub s and make adjustments until they converge. So we're going to do an assumed temperature here. We're going to assume our T of s is equal to 45 degrees Celsius. So with that assumption there, we also have our T sub infinity is 25 degrees Celsius given to us in the problem statement. So now again, we said we're going to do the average temperature. When we look this up, table C, table A4. So we're going to take 45 plus 25 divided by 2, and this will give us our average temperature value of 35 degrees Celsius. Now for our table, we're going to want this in K, so this is going to be 308 K. So now we're going to take T average, go to table A4, and use this to get our properties for air. So now we can go to table A4. A4 is the thermophysical properties of gases at atmospheric pressure. Now we have our temperatures in Kelvin over here, and we have all of our properties over here to the right. Now what we need to do is to do some interpolation, because we can see that our temperature that we just solved for our average temperature based upon the assumed T sub s is a value of 308. Now 308 does not exist here. We have 300 and 350. So we need to do some interpolation to figure this out. So for interpolation, I use this relationship down here, where I have that y2, which is our interest of whatever property we have here, is equal to x2 minus x1, where x2 is our 308, and x1 is our lower end of this here, times y3 minus y1, where y3 is our value here, and y1 is our value here, all divided by x3 minus x1, so our upper and lower limits there, plus our y1 value there. So we can go through and plug in our known values into this relationship here. So what we're looking for in this case here is our K value. So if we solve this for our K value here, we can plug in our known values here. So 308 minus 300, which is our assumed temperature value, minus our lower limit value, times 30 minus 26.3. There's your 30 minus 26.3 there. All divided by 350 minus 300, the upper limit, the lower limit here, plus our value for our y1 there, which is 26.3. Plug this in, and we can now get a K value of 26.892 times 10 to the negative third. And we look up at our units there, and we can realize we can rewrite this as K is equal to 0.0269. Now we can do the same thing for our other properties in the table. We're solving for V here. So V is equal to our, again, our temperature of assumed 308 minus 300, our lower limit there, times now our Y values for this guy over here for our V, which is our 20.92 and our 15.89, divided by our upper and lower temperature limits, 350 minus 300 plus our 15.89. We get a value here of 16.69 times 10 to the negative 6 when we interpolate. And lastly, we can do the same exact thing for our PR number. So PR is equal to, again, our temperature of assumed, our TS here, 308 minus our lower limit of 300, times our 0.7 minus 0.707 for our values for our PR upper and lower, divided by our upper and lower temperatures, 350 minus 300, plus that 0.707 over here. So we get our PR is equal to 0.7058. So now we have all of these properties for our assumed temperature of 308 for T sub s. So we now have a K, V, and PR values for our air at assumed temperature at the chip surface from table A4. So we have our K value is equal to 0.0269 in units of watts per meters times Kelvin. V is equal to 16.69 times 10 to the negative 6 in meters squared per second. And our PR number is equal to 0.7058. So the next thing we want to do is perform an energy balance on the chip. So Q convection is equal to our E sub G dot. So Q convection is equal to, which is given the problem statement here for E sub G dot, of 30 milliwatts. So from there, we can now use Newton's law of cooling, which we recall that Q is equal to AH times our temperature difference, so TS minus T infinity. Now we can rearrange and solve this for our TS, our surface temperature here. So when we do this here, our surface temperature T sub S is equal to our surrounding ambient air temperature T infinity plus our Q convection all over H times A chip, where A of the chip is L squared. This is a square chip. So the next part of our solution, we need to assume that this average heat transfer coefficient, our H bar here from our previous equation, over the chip surface is equivalent to the local coefficient evaluated at x is equal to L at the location of that chip from the leading edge. So from that, we have the equation that, again, our average heat transfer coefficient H of our chip is approximately equal to H sub x at location L. So now we can reference back to equation 6.48 in our textbook, where we have our Nu sub x is equal to our, this is from right above here, our H sub x L divided by our K value here. So now we can plug this into our given equation from the problem statement. So if we can take this value here, where we now have this H sub x of L at location L divided by K, plug that in for Nu sub x here back in the given equation. So we can then use this as equal to, when we plug this in, 0.04 times our Reynolds number sub x to the 0.85 times PR to the 1/3. So with this here, what we want to do now is solve this for H of L. So we can rearrange slightly within this guy here, and we can pull this K over L, reverse it over, divide it from this side, put it over on this side. So now we have our H of L, or H of x at L, and we plug this in here is equal to K over L, and we move it over, times our 0.04 times this RE sub x to the 0.85 times our PR to the 1/3, where this RE sub x is equal to Vx over V, or in our case here, VL over V, when we plug this in when x is equal to L. So now we can rewrite that equation. We have H sub L is equal to our K over our L times our 0.04 times VL over V, where we have this to the 0.85 times our PR to the 1/3. Now we have our known values. So write down all our known values you want to plug in here. We have K as 0.0269 watts per meters times Kelvin. We have our L is equal to 0.12 in meters. We have our V is equal to 10 meters per second. We have our little v here is equal to 16.69 times 10 to the negative 6 meters squared per second for our units, and our PR value of 0.7058. So now that we have these values either from the given problem statement or from our lookup from the table, we can plug back into this above equation here. And that's what we do here. H sub L is equal to our 0.0269 watts per meters times Kelvin divided by our L value of 0.12 meters times 0.04 times our 10 meters per second times 0.12 meters divided now by 16.69 times 10 to the negative 6 in meters squared per second, all to the 0.85 power times our 0.7058 to the 1/3 power. We can break this down. This term right here breaks down to 0.08967. Then we have 13,434.355 times our 0.8914. Or we could have plugged this all into MATLAB, Excel, or our calculator, and we end up getting a value of H of L is equal to 107.3. Now we can take this H of L and plug back into our TS equation here. We have TS is equal to T infinity plus our Q convection over our average H times the area of our chip here. So we recall that equation. We can plug back into that. We do that for these specific values here. So that's what we have here now, is we can plug back into that. So our T infinity was given to us as 25 degrees Celsius. Plug in our values here for our Q convection of 30 times 10 to the negative 3rd watts. Our H value of 107 watts per meter squared times Kelvin, and our area of the chip, when we do that outer length times the length there, of 0.004 meters all squared there. And now what we have is our T sub S is equal to 42.5 degrees Celsius. So now we go back to what we assumed for a temperature, so the estimated value of T average is reasonable. Now if these weren't close, 42 and 45, maybe this was ended up being 100 or something, we'd need to go back, repeat this problem, and converge between the two, our assumed and our final answer, until we did converge on something that was close. So this is reasonable, so this estimated value we can stick with.
So as you saw in my hand solution, there's several tables that I referenced to. This is one of them, our table A4. So within this is the thermophysical properties of gases and atmospheric pressure. So I wanted to include this in the video as well as in the PDF that I'll be posting to Blackboard as well. So as you're following along and doing out these problems by hand, you can reference back to this, look where it is in the textbook, and then understand what I did, where I came up with all my variables, see all my governing equations as related to this table here, all in one spot. So now let's go through another example problem. So I'm going to go through my hand solution to this problem number 6.64 in our textbook. Again, please follow along, do this one out by hand with me, reference back to everything that I talk about within this problem in your textbook, and then you'll understand exactly where to go as we're going through this solution when you're preparing for your exam number 2. So within this problem here, it also references to this problem 6.63, so I've included this problem statement as well for you to reference. So here is that problem 6.63 that's referenced in 6.64. A lot of times the textbook does this, so please make sure you go back and reference everything in this. And there's even problems that reference another problem, that reference a table, that reference another problem, so on and so forth. And this is something that is important because as you go further and further along in your curriculum, you start doing some research grants, you start working for a company, a lot of times that is going to be the real world, where not everything is given to you in the one problem statement. You've got to keep digging deeper and deeper to get all the information you need to solve the problem at hand.
Let's take a look now at problem 6.64. In this problem here, they're asking us to consider an application of the naphthalene sublimation technique, which we've seen in problem 6.63, which we'll review back to get some of our variables. But now they want us to do this to a gas turbine blade that is coated with this naphthalene. It has a surface area of A sub S is equal to 0.05 meters squared. And they show down below here's our given schematic where we have our airflow, our V, and our T sub infinity. And here's our blade with the coating on it and all the associated properties there. So now let's take a second and go back to problem 6.63 and see if we can get some more of the information from this problem. So now let's reference back to this problem 6.63, which they refer to in our problem 6.64. So in this problem here, we have that the naphthalene sublimation technique involves the use of mass transfer experiment coupled with an analysis based on the heat and mass transfer analogy to obtain local or average convection heat transfer coefficients for complex surface geometries. Now I have a coating of naphthalene, which is a volatile solid at room temperature, is applied to the surface and is then subjected to airflow in a wind tunnel. Alternatively, solid objects may be cast from this liquid naphthalene. After a designated time interval, some delta T, there is a discernible loss of naphthalene due to sublimation. And by measuring the surface recession at locations of interest, or the mass lost of the sample, local or average mass transfer coefficients may then be determined. So for this problem here, they wanted us to consider a rectangular rod of naphthalene exposed to air in cross flow at V is equal to 10 meters per second. Our T sub infinity is equal to 300 K, as in problem 6.10. So now they're referencing back to another problem. So I would suggest taking a look back at this as well. Except now our C is given to us as 10 millimeters, our D as 30 millimeters, and they ask us to determine the change in mass of the L is equal to a 500 millimeter long rod over a time period of delta T is equal to 30 minutes. Now, naphthalene has a molecular weight given to us as 128.16 kilograms per kilomole, and its vapor, solid vapor, saturation pressure at 27 degrees Celsius and 1 atm is given to us as Psat of 1.33 times 10 to the negative 4 bar. So now that we've had a chance to reference back to problem 6.63 to see this technique, the next thing we want to do is figure out what they're asking us to solve for in our problem here. So they want us to determine the average convection heat transfer coefficient for a representative operating condition. An experiment is performed in which the coated blade is exposed for 30 minutes to atmospheric air at the desired velocity and temperature of T infinity is equal to 27 degrees Celsius. During the experiment, the surface temperature is T sub s, given to us now as T sub s equals 27 degrees Celsius. And at its conclusion, the mass of the blade is now reduced by this change in mass, delta M is equal to 8 grams. They want us to find the average convection heat transfer coefficient associated with the operating condition. So based on the information here and what we've seen from our definition of this technique back in problem 6.63, we have enough information to start the problem. So now that we've had a chance to read through the problem statement for problem 6.64, look at the given schematic, then reference back to problem 6.63, we have a lot of information given to us between those two problems. So what we really want to do is write out everything that we know. What are the variables? What is the values? What are the units? All this information, figure out what they're asking us to solve for, and what assumptions we're going to make in order to come up with a solution. So as we slowly go through these, we have our A sub s is equal to 0.05 meters squared. Our surface temperature, T sub s, is equal to 27 degrees Celsius. Or I'm going to convert to Kelvin here, and this is going to be 300.15 K. We have our T sub infinity is equal to 27 degrees Celsius as well, which again is 300.15 K. And then from problem 6.63, we know that P is equal to 1 atm. We also know from that same problem that P sub A comma SAT, or saturated there, is equal to 1.33 times 10 to the negative fourth bars. Again, pay attention to our units when we go to plug in for our actual equations. Our delta T was given to us in that same problem, 6.63 is 30 minutes. In our new problem, we have our delta M is equal to 8 grams. So for this problem here, we know our delta M. And we have our molecular weight given to us in problem 6.63 is 128.16 kilograms per kilomole. Now they want us to find the average convection heat transfer coefficient associated with the operating condition. So this is our H bar that we're looking for here. Assumptions that we're going to make in this problem here, we're going to assume applicability of the heat and mass transfer analogy. We're going to assume negligible changes in AS due to mass loss. We're going to assume that naphthalene vapor behaves as an ideal gas. We're also going to assume that the solid vapor equilibrium at surface of the coating occur at the surface of the coating. And we're going to assume negligible vapor density in the free stream airflow. So based on these 5 assumptions, we can now come up with a method for our solution. So for our plan for the solution to this problem, the first thing we need to do is to go to table A4 and look up the properties of air at this known temperature of 300 K or 27 degrees Celsius. So when we do that, we can get all of our values here. So let's go to table A4 and look this up. So now let's go to table A4. We can look up our thermophysical properties of gases at atmospheric pressure, which is for our case here 1 atm. And now we have our temperature for us here is at 300 K. So I boxed this in all the way across for all of our properties at a temperature of 300 K, which is given to us. So we get our mass density, our specific heat, and we're also looking over here for our value now for our thermal diffusivity. So we can get all 3 of those values here from table A4. So once we have those values, the next thing we're also going to want to do is to head to table A8 and look up our properties here. Our binary diffusion coefficient is at 1 atm. For our substrate here, our substance A here, naphthalene, substance B is air, temperature is 300 K. So now we have our DAB in units of meters squared per second here of 0.62 times 10 to the negative 5. So from tables A4 and A8, we're now able to get all the properties that we need in order to begin our solution to this problem. So now we've had a chance to get the information from table A4 and A8 in our textbook. Again, we looked up A4 at a temperature of 300 K. We're able to get our mass density here. Rho is equal to 1.161 kilograms per meters cubed. Our specific heat we found is C sub P is equal to 1007 in units of joules per kilogram times Kelvin, and our thermal diffusivity is equal to 22.5 times 10 to the negative 6 in units of meters squared per second. Then we also went to table A8 for naphthalene, and we looked up here, we wanted to find our binary diffusion coefficient at this 1 atm. So we found this, d sub AB is equal to 0.62 times 10 to the negative 5th in units of meters squared per second. Now, from the rate equation for convection mass transfer, we have that the average convection mass transfer coefficient may be expressed by the following. And where this comes from equation 6.19 on page 384 of our textbook. So this H sub m bar is equal to our mass transfer rate here divided by A sub s times the difference here, where now a difference our densities here, where now we want to say this is equal to and equivalent to our delta m over delta t divided by A sub s times our rho density times A for A comma S. So we know here our values for delta M and delta T are given in the problem statement. So now we need to figure out what we can do with these guys here. So we take a look at here our density A comma S here. So this is equal to, for our specific problem, a value of our density A comma saturated, which we have in our problem statement here, which is equal to our molecular weight times this constant C A comma S here, where the C A comma S is given to us by the definition over here for P saturated, or density saturated, times our surface temperature T sub S, divided by this universal gas constant here, times T sub S. And this comes from equation 6.22 on 384 as well. So we have a lot of equations within equations here. Some of our variables are going to be known, some we need to reference back for, some we need to solve for. So let's try to organize this a little bit more in our next section. So now we can break this down and look at each individual part of this. So we have our density sub A comma S is equal to our molecular weight times this density of A comma saturated, all divided by our universal gas constant times the surface temperature T sub S. Where now we have a value for this universal gas constant as 0.08314 in units of meters squared times bar divided by kilomoles times Kelvin. So if we plug in our known values into this relationship here, we now get their density comma A sub S is equal to 128.16 for molecular weight, units of kilograms per kilomole. Now our density here is given to us as 1.33 times 10 to the negative 4th in units of bar. And now we have on the bottom side here, we have our universal gas constant, again, those same units of meters cubed times bar over kilomoles times Kelvin. And then we have our T sub S and Kelvin there. So we can go through and do some unit analysis. Our bars and our bars, our kilomoles and kilomoles, kelvins and kelvins. This cancels out, and what it leaves us in is kilograms per meters cubed, which is exactly what you expect for this density here. So we plug this in, density of sub A comma S is equal to 6.83 times 10 to the negative 4th kilograms per meter cubed. So from this point here, what we want to do is plug this value back in to our bar, H sub m bar equation. So recall that there, we will rewrite this down here. H sub m bar is equal to our N sub A, all divided by A sub S, times our difference in our densities here. So we have a lot of information here that we already know. So we have this here, our N sub A as our mass rate, has units of kilograms per second. Our delta M term over here, we recall, is 8 grams, or we convert to kilograms of 0.008 kilograms. Our delta T is in 30 minutes. So we can plug this in, rearrange this into the equivalent here. Recall from that equation, this is equal to delta M over delta T divided by our density of A comma S times our AS there. Plug in our known values. Our delta M is equal to this 0.008 kilograms. Our delta T is 30 minutes. Convert this now down to seconds here. So 60 seconds per minute. Do our unit conversion. Times our rho sub AS that we've just solved for above here is 6.83 times 10 to the negative 4th kilograms per meters cubed. And our A sub S for our problem here is 0.05 meters squared. Do out our unit analysis here, we end up in meters per second over here. So our H sub M is equal to 0.13 units of meters per second.